To continue talking about colligative properties, our third colligative property is freezing point depression. It is exactly what it says. It depresses or it lowers the freezing point of your solvent. If we take a look up here at this phase diagram up here, this line here is showing the normal phase diagram of a certain solvent, probably water, while this line here shows the new phase diagram whenever you put in a solute like salt or sugar or something like that. Notice what happens to the normal. Remember, normal means at sea level. The normal melting point, it gets lowered. The normal boiling point gets raised. Case of boiling point, elevation, freezing point, which freezing point and melting point are the same thing. Freezing point, depression. This is true for all solvents. When you put a non-volatile solute into them, the phase diagram will change in the same way. If we look down here at this formula, notice that this formula is exactly the same as the boiling point elevation formula. Exactly the same. And it works exactly the same way. You got your change in temperature and freezing point this time. You've got Kf, which is your freezing point constant. Same sort of thing. You either look it up, they'll give it to you, or you're going to end up solving for it. And again, we got molality of our solute in the solution. Look at this question here. Why does adding salt on a sidewalk prevent ice from forming? The key here, guys, is that ice can still form, but the salt causes the freezing point to lower. So instead of forming at 0 degrees Celsius, it will now form at -5 degrees Celsius, -10 degrees Celsius. So unless the temperature drops even more than it already is, then it can't freeze. So if you have really, really, really cold temperatures, putting salt or something on the sidewalk isn't going to help a whole lot, but it helps for temperatures like we have here in Oklahoma. Why is it useful to use calcium chloride instead of sodium chloride? We've talked about this a little bit. Calcium chloride breaks apart into 3 moles of particles for every mole of calcium chloride that you use. So if I use a mole of NaCl and a mole of CaCl2, I'm going to get more freezing point depression from the CaCl2 because it forms more moles of particles. So let's take a look at this last problem here. Which of the following would produce the largest depression in freezing point when added to 1 kilogram of water? Pause this and try it yourself real quick, and then turn it back on and see if you got it right. The key is how many moles of particles does this form? Cobalt nitrate, this is a soluble ionic compound. If I dump 1 mole of this into solution, it's going to form 1 cobalt and 2 nitrates. So it's going to form a total of 3 moles of particles. If I put 2 moles of KCl dissociates into 2 particles, so 2 times 2, this is going to form 4 moles of particles. Or 3 moles of ethanol. Ethanol is an organic compound. It is not going to dissociate, and so it is just going to form 3 moles of particles. So 2 moles of KCl is going to have the greatest freezing point depression or boiling point elevation when you put it into water, because you're putting the more moles of solute particles into the water. The last colligative property we're going to look at is osmotic pressure. Osmosis, y'all guys know what this is. It's the movement of water from an area of high concentration to an area of low concentration. And one way to look at that is by using this diagram right here. This diagram is showing a pure solvent and a solution, so maybe some sugar water or salt water or something like that, and a semi-permeable membrane separating the two of them. The semi-permeable membrane will let water through, but it won't let the solute through, so it won't let the salt or the sugar through. Another way of looking at this is on this side of the semi-permeable membrane is 100% water. Over here in the solution side is going to be less than 100%. I'm just going to make up some number, 80% water. All right. And so since water naturally moves from an area of higher concentration to lower concentration, it's going to move through the semi-permeable membrane over to here. And it's going to do that to try to dilute the solution. And when that happens, the water level lowers and the solution level raises because it's getting more and more water over here. The definition of osmotic pressure is how much pressure would you have to apply to this solution right here, push it down to force that water to go back through the semi-permeable membrane and even out these levels again. All right, this is what we call osmotic pressure, the pressure necessary to keep that water from flowing across the semi-permeable membrane. This equation right here is the osmotic pressure equation, where the pi symbol is a symbol for osmotic pressure. It is in atmospheres, where m is molarity, where r is our gas constant, same gas constant that we used in our gas pressure problems, and then T is our temperature in Kelvin. This equation over here is just a different variation of this, and notice what it looks like. You got pressure, volume, moles, RT. It's a PV equals nRT equation, and all that is just a different variation of this equation right here, because molarity is moles over volume. So if you take moles over volume and switch it around a little bit, you get this right here, moles over here, volume over here. And so it's just PV equals nRT in a different form. So let's take a look at this problem right here. It says the osmotic pressure of an aqueous solution is measured. The solution contains 3.5 milligrams of some protein dissolved in water to make a 5 milliliter solution. The osmotic pressure is found to be 1.54 torr. We want to know what's the molar mass. Why don't you pause this, go ahead and see if you can solve this yourself. It's very similar to our other molar mass problems that we have done. One with vapor pressure, one with boiling point elevation. See if you can figure out how to solve this, and then turn back on and see if you got it right. One way to do this is to start out with our osmotic pressure equation. Remember that the pressure needs to be in ATM, so I got to take that torr, divide it by 760 to turn it into ATMs. I don't know the molarity because I don't know the moles, but I do know the volume is 0.005 liters, or 5 milliliters. We know R's 0.08206. We know temperature is 25 plus 273. We go through and solve for this. We're going to get somewhere around 4.14 times 10 to the negative 7th moles. Now we got moles. We know the mass is 3.5 milligrams. Be sure and change that to grams. We know molar mass is grams per mole, so we take our grams, we divide it by our moles, and we get a really, really, really big molar mass. Now normally if you get a molar mass that looks like this, really big, that would be a chance to stop and check and make sure that what you got actually made sense. Now this is a protein, and proteins are huge molecules, so it does make sense that we would get an incredibly large molar mass here. The rest of this stuff in this little section here on osmotic pressure may not be that important. Dialysis is a process that's used in medical procedures to clean out the blood, and it uses osmotic pressure. In biology, you talk about isotonic, hypertonic, and hypotonic solutions. And isotonic solutions, these are solutions that have the same osmotic pressure, so you don't have to worry about things absorbing too much water or letting out too much water. If they let out a lot of water, this is called crenation. This is when the cells will release a lot of water, and they'll start to shrivel and shrink. Hemolysis happens whenever the cells take in a lot of water, and sometimes they can burst. They can actually blow up. This can happen with with blood cells sometimes, which is really interesting. And I'm going to skip to, let's see here. I'm going to skip here to letter A. There's a big difference between what is expected with colligative properties and what is actually observed in colligative properties. Whenever you have ions moving around in a solution, sometimes they'll run into each other and they'll stick together. And when that happens, you remove some of the ion attractions to water molecules, and so the number of particles reduces, and that also means that the effect that they're having on the water molecules reduces as well. Now what you can use to figure out how much it's being reduced by is by something called the Van 't Hoff factor. The Van 't Hoff factor is abbreviated with letter I, and it's the moles of particles in solution divided by the moles of the solute that is dissolved. Now, theoretically, you can figure out the Van 't Hoff factor just by knowing how much it's going to dissociate by. So, like NaCl forms NaCl forms 2 particles for every 1 particle of sodium chloride. So we would say its value for I, its value for its Van 't Hoff factor should be 2. BaCl2, it should be 3. Al2SO4, 3 should be 5. Right, that's how many particles it actually forms. However, because of that thing where the ions are constantly moving around and sometimes interact with each other, and sometimes they attract each other so that they are less likely to actually affect the water particles, the values for I are almost always lower than expected due to ion pairing. And the more they run into each other, the lower and lower it gets. So that means the values for I get closer to the expected number when you have really, really dilute solutions. But when you have super concentrated solutions, they run into each other more often, and the values for I become less and less correct. Now, you can incorporate the Van 't Hoff factor. You can incorporate I into these equations. Just like this, it's the exact same equations that we had before. You just put the letter I in there, and they're really easy to deal with. Sometimes you don't even have to write it down. Just keep in mind, oh, it's NaCl. That means it'll lower the temperature twice as much as I'm expecting. So let's take a look at this last example here. In this problem, we have 5.5 grams of NaCl being mixed with 100 milliliters of water. It tells us the freezing point goes from 0 to negative 3.3. It gives us Kf of water. It wants what's the value for I for NaCl. And what does this tell you about the percent dissociation? Now, we would expect the value for I for NaCl to be 2. We know, however, it's going to be a little bit lower than that. So we can use our equation to figure out how much lower it's going to be. So why don't you go ahead, pause this, try it yourself, and then we'll check and see if you got it right. Okay, the equation we're going to use is just our freezing point depression equation with I in it. When we start plugging in numbers, we're going to have to figure out what the moles of the NaCl are over kilograms of solvent. So when we do that, we take that 5.5 grams of NaCl, divide that by the molar mass. We find moles of solute, so moles of NaCl is about 0.94, over kilograms of solvent, 0.1 kilograms. And so we get for our value for I to be 1.89. Now again, we would expect to be 2, so there is a little bit of ion pairing going on here. To find the last part, what's the percent dissociation? Just take, the amount it really dissociated by, divided by the amount that you think it probably should dissociate by, 2. Multiply it by 100, because it's a percentage, and this is about 94.4% dissociation. If it was 100% dissociation, then I would be equal to exactly 2. But that will only happen if you have an incredibly dilute solution.